Oh, I see why I was having a problem. I was looking at 2.50. Because it was a different problem on the 2.2.
Okay. Section 2.5, we're going to calculate the multiplicity of an monatomic ideal gas.
You're out of frame.
What's that?
You were out
Out of the frame?
Yeah.
I know.
of. Oh, okay.
I wanted to show the horizontal.
Sorry.
Although, yeah, I'm close on that. All right, and to tell you the truth, this is one of my favorite derivations in the book. It's about the right length to follow at one sitting. It's got some, a little bit of complexity to it, but there's a nice, elegant way that it comes out, using things that you mostly already know. Okay, so remember the multiplicity is the number of distinct states the system can be in. And so we're going to count up how many ways how many different states the system can be in. So we're going to start with a system of a single atom, and we're going to make it where it's a monatomic gas. So the atom is by itself. It has no spin or vibration. We're not going to worry about those. The only things we can really get to what the states will be made out of. We're going to have a single atom at first. So N equals 1. And let's say that we know the kinetic energy, or let's say we know the total energy. And we have a container with a known volume, V. When you make a V for volume, make sure it's capital, and I would recommend putting serifs on it to distinguish it from lowercase v, which will usually mean velocity. Okay, so the multiplicity is counting the number of microstates that the atom can be in given a fixed energy and volume. So here's the thing. Get out my book for the first part of it here. Let's see. When we had our two-state systems, like the two-state paramagnet, what were for a single particle in a paramagnet, what were the two states it could be in?
Transitional and...
Nope. Simpler than that. Paramagnet had like a little compass needle. So the state depends on which way it's pointing, but there are only two states available. What do we call those? Up or down. And that was it. And like I said, blatantly simple. It can either be pointing up or it can be pointing down, and those are the only things it can do. So the two-state system was easy because there were two states. Now we've got a gas in a box. An actual particle bouncing around the box. Think for a second. What are the states? Again, what are the variables that describe its state? We're not thinking about macroscopic ones now, temperature, energy, volume. Those are not the states. What is the state that describes the conditions of a single particle? What variables go into that?
How it vibrates, the direction of...
Nope, it can't vibrate. It's a single particle. It's not in a molecule. Its position is one thing. All right, so it can be here or here or here or here or here. All right, it can have different positions. Those are different states for it. What else? It can be somewhere. It could also be doing some things. What could it be doing?
Vibrating, spinning?
No, not vibrating. No. It's not in a diatomic molecule.
Okay.
but it can have motion. It's got a box to run around in. So what about what can it be doing that can make it be different from when it's doing something else? Well, it can be moving, right? This way or that way or this way. In fact, so it's got momentum. Now, I could say that it's got velocity, but given a certain mass, remember that momentum is mass times velocity, and in practice, we're, in many cases, interested more in the momentum than the velocity. But the two are really tied together. You just multiply by mass to get momentum. These are the two things that will describe its state for one particle. Okay, so multiplicity, we use capital omega. If we have a larger container, a larger volume, then it's got more room to be in. And that means that there are more positions it could be in, and therefore more states it could be in, right? Okay, so the larger the volume we've got, the more positions it can be in, and therefore the larger the multiplicity. So it makes sense for the multiplicity to be proportional to the volume. Think of this, if the container we've got, the box, is twice as large, it has twice the number of places available for the particle to be in, and therefore twice the multiplicity. So, proportional. I haven't got the concept of proportionality, but I know it's proportional. And think here how we graph this. Positions have 3 dimensions. X, Y, and Z. So we'll just call this a normal space. Really, we can put a label on it. We can call it position space. Okay. So if we've got some kind of a boundary here in its positions, those are the walls of the box. So we've got some volume here that I've drawn out, and it can be anywhere within this here, right? Anywhere. This is our round box here. This defines the volume. That's the volume there. It can be anywhere within there, any one of those position states within that. What about the momentum? The momentum, a little trickier. But while position has x, y, and z components, 3-dimensional vector, so its position, r we use for position, so it has x, y, and z components to r. The momentum can be expressed in a similar way. We can write out a momentum space. Okay, px, py, pz. So, how many ways, how many different states of momentum can that thing be in? Now, here we get into a little bit of the concept gets slightly trickier. P equals mv. P is the momentum. V is the velocity, lowercase v. So it can be moving with some speed in a certain direction, and given its mass, that gives it its total momentum. Now, if I've got, maybe it's moving, there's its momentum vector, like that. Maybe it's moving up and to the right at a certain speed with a certain momentum. So the speed, and therefore the total momentum, gives me the length of the vector, the magnitude of that, and the direction gives me the direction of the vector. So all the combinations of how fast it's moving and in what direction give me all the different momentum states it can be in. Does this make sense? If it's moving a bit faster, that's a different state. If it's moving in a different direction, that's a different state. Or a little slower, that's another state. Reverse the direction, that's another state still, and so on. So you see that you've got all these different possible directions it can be moving and how fast. And again, you multiply by momentum, you get multiply by mass, you get the momentum. Okay, so I've got some amount of momentum it can have in x, in y, and in z. So, fortunately my notes are upside down here. How much momentum space is really available to it? Well, the thing is, we've got, let me put it this way here. It could, for a given amount of momentum, it could be pointing in any direction. Like that. So we have some, the momentum vector for moving at a certain speed with its mass. That defines the length of this vector, and then you have all kinds of range of directions it could be pointing. And this gives you a volume in momentum space. Here's the math of this. Let's see here. Now, we've got position space and a volume we let it run around in position. We've got momentum space and what that volume is. This is an abstract kind of space, really. So we'll talk about a momentum space volume in P, or momentum space, there. So the multiplicity should be proportional to the product of those two. If you've got double the amount of momentum states available, you double the multiplicity. If you double the number of position states available, you double the multiplicity. Works both ways. And again, we're dealing with a single particle. I should subscript that. Okay. Now, to get beyond this, space here. What we're actually measuring on the particle is going to be its energy. So how does that relate to constraining this? If we've got a box of volume V, we know the volume, then we know the constraints on the position space it's got available. But how do we constrain the momentum space it has available? By knowing its energy. Capital U is the total energy. Energy is made up of kinetic and potential. KE and PE, at least I'm going to abbreviate them this way for now. We'll change symbols later on in the book. An ideal gas, a monatomic ideal gas. One of the rules of an ideal gas is that the particles of the gas do not interact with each other until they bounce off. So there's no potential energy between the particles. You don't have like, if you had a strong electrical charge on two particles so that they were pushing each other apart or pulling each other in without actually touching, that would give you some potential energy between them. We don't have that. You might also think, well, what about the potential energy from gravity? Like we're doing this in a laboratory, so we're on the Earth, we've got a gravitational pull. Yes, they have a gravitational potential energy, but unless you're talking about the difference in the gravitational pull between being down here on the ground and being way up at the upper edge of the atmosphere, well, there's not a whole lot of difference if you're within this room, say. The gravitational potential energy at the bottom of the floor and at the top of the ceiling is about the same for something with so little mass as a single particle. So the potential energy is essentially the same everywhere, and only differences of potential energy matter. So we can completely ignore potential energy from this. All we care about is kinetic energy. What's the formula for kinetic energy? 1/2 mv squared. Right. What's the formula for momentum? mv. Let's put the two together. So v equals p over m. And if we put that in there, we get the kinetic energy is p squared over 2m. This is a really useful formula for kinetic energy. You're going to use that not only in thermodynamics, but it's used in quantum mechanics, you use it in physical chemistry, it's used in classical mechanics and so on. Because in many cases, we're interested in the energy for certain reasons of conservation laws for energy, and we're interested in momentum because there's a conservation of momentum. So these are two important things there. Now, that means, since the total energy is just kinetic in this case, total energy is p squared over 2m. Okay. If I know the total energy of the particle, we got one particle now, that means I know its total momentum. So, let's see here. Multiply through by 2m's, take the square root. So in momentum space, the limit, the boundaries of the momentum space are given by the length of the momentum vector, p, which itself is given by the kinetic energy, which is given by the total energy. So here I can get rid of the vector symbol. That p there is the total momentum. This is the radius of a sphere in this momentum space, as I'm calling it. So if I know the energy, I know the radius of that sphere, which gives me the volume. There's a little subtlety to it, though. Let me get this over to another board. Let's say this is the first part. You see that zoom in more. The zoom seems to have changed. Interesting. That's my volume in momentum space. Well, but notice what that constraint is. If I know, okay, there's the total momentum, P, and I know that, let's see here, P squared over 2m, all right, there we go. But P has components in x, y, and z. So how do I get that out of the individual components? I've got 3 dimensions here. Well, the Pythagorean theorem applies. If all I had were 2 dimensions, x and y, the length of a vector is the hypotenuse of a right triangle. Your coordinate axes are at right angles to each other. If you had just 2 dimensions, and you had a total length P, Px and Py are related as the sides of a right triangle. So the hypotenuse, P, would be equal to the square root of the sum of the squares. Square root of Px squared plus Py squared. Take the square root of the whole thing. But in 3 dimensions, we've got exactly the same thing. The Pythagorean theorem extends to multiple dimensions. So P squared equals Px squared plus Py squared plus Pz squared. Okay, now that's a nice thing there. That breaks down very nicely. And let's see here. I want to get a formula for the volume of this position space. I've already got the volume of momentum space, but that's something that's known. How do I get the volume of momentum, position space? How do I get the volume of momentum space? All right, so that's there. Now, let me multiply both sides by 2m. And I'll, let's see. Let me rewrite this side. Yeah. I'm going to write 3 sides to this equation. There we go. Multiply all sides by 2m. Take the square root. Okay, now I wrote it with 3 sides just so that I can illustrate something while at the same time solving. The volume is defined by what that momentum is. But what I actually know is the total energy. That's what I've got measured. That's a macroscopic thing there. The radius of this circle, of this sphere, is P, and it breaks down into these components here. All right. But whereas when we were dealing with position space, the volume, the particle could be anywhere within that volume, right? If it has a certain defined momentum, because it's got a defined energy, can it be anywhere within this sphere? It's sort of a trick question, by the way. How would it be inside the sphere? It would have to have if I say, here's a sphere, let me make it a circle for a moment so I can show you here. Just a circle. It has a radius p. Well, that gets you to the surface of the circle, the edge of the circle. If I'm saying, can it be inside it, the distance from the center has to be less than the radius of the circle, doesn't it? To be inside that. So, what this is telling me is that the so-called volume is really just the surface of a sphere in momentum space. It can't be deep inside there because that would mean it had less momentum than what I said it had. All these different directions the momentum vector can point are still making it stick onto the surface of that sphere. So the volume that I'm talking about is actually the surface area times, well, quantum mechanics says that we have some uncertainty in our measurement, our knowledge, in fact, of the actual case, state of the energy and therefore the momentum. So there's a little bit of uncertainty. There's sort of a thickness to that skin on the surface. It can be a little bit more, a little bit less, and there's no way for us to know the difference. So we've really got just that little bit of thickness, a skin on that sphere. We've got sort of a shell there running around, if that makes sense. And even if it doesn't, we'll have to go on with it. Okay, so the actual volume is the surface area times the uncertainty in the momentum. Now, the really tricky part comes in trying to count the number of microstates, the number of individual states that this particle can take. I've said that each different position it can be in is another state. Each different momentum it can have is another state. But when we had our two-state system, we could count the states, up or down, 1, 2. There was no in-between there. So you just had one or the other. But what if you've got a particle, there's its position, range of positions x. There's one state, it's here. Here's another state, another state, another state, another state. How many different states are there here? X varies continuously, so how many different places are there between here and here? And an infinite number of possible places. The same thing with momentum. There's an infinite, for a given length of that vector, there's an infinite number of directions it can point, mathematically. Although it does seem obvious that if the multiplicity is proportional to this volume, which is really the surface area times a little thickness, well, the larger that vector is, the more surface area there is. So it seems like I've got either an infinite number or a more infinite number, which doesn't make sense. But these things vary continuously, so how do we count them? Multiplicity is the number, actual number of different states. How can we count up an infinite number of these things? Quantum mechanics gives us a way out. It actually allows us to do this, because quantum mechanics quantizes things that we otherwise would have thought were continuously varying. This is the really clever part of this, I believe. Okay. The reason this is possible is because after, let's see, you've heard of quantum mechanics began about 1899, when Max Planck, P-L-A-N-C-K, figured out that energy was emitted from hot objects in discrete packets, quanta of energy. Hence why we use Q for the quanta of energy in an Einstein solid. So energy was quantized. Then, that seemed to argue that, well, light was made out of particles. but it was well established already that light was made out of waves, because we can get diffraction patterns, interference, and so on. So Max Planck was not totally convinced that what he had done was physically real, or maybe that it wasn't a fundamental property of nature. Maybe it was just a trick of how light happened to be emitted in those cases, that it was in discrete units, because clearly light was a wave, right? Einstein, however, took Planck maybe more seriously than Planck took himself. This is sometimes the case in physics. And Einstein, in 1905, argued that light was both a particle and a wave, simultaneously. Now, those properties seem to contradict each other. And so there's an enormous amount of philosophizing in physics about the meaning of the wave-particle duality of light. And we still haven't totally resolved it. Now, in the 1920s, early 1920s, Louis de Broglie and he's French, so you've got to not pronounce half the letters. Louis de Broglie was a French prince, actually. Although they didn't recognize princes then, they still kind of carry their titles. Louis de Broglie was a French prince who was working on his PhD in physics, and he was thinking, okay, Planck comes up with the particle nature of light. We already know about the wave nature of light. Einstein takes that seriously, unifies the idea of particle-wave duality with all of its weird consequences. And so if light is both particle and wave, de Broglie thought, what about matter? Things that have mass. In fact, he was thinking, maybe light has mass, a very, very tiny amount of mass. So if light can have a wave, what about things that have more mass, like electrons, protons, neutrons, us, for example? Maybe we have waves as well that we act as. So he talked about the wave nature, the wave function of matter. His dissertation advisor rejected it, thought it was a load of nonsense. De Broglie took the step, now remember he's in his 20s at this point, writes to Albert Einstein, sends him his dissertation work, and Einstein writes back to his dissertation advisor and says, no, this is real. I'm annoyed that I didn't think of this myself. And he wound up getting his PhD, and this was the big step forward in quantum mechanics. One of the few major steps forward in quantum mechanics. The wave-particle duality of matter. Well, what is a matter wave? It turns out that the matter waves are waves of probability. It tells you where a particle is likely to be at some given point, at some time. Now, it doesn't always look like an ocean wave, with just this sort of nice sine wave or cosine wave function. Sometimes it does. Other times, in many cases, a matter wave looks like, let's see if I've got room here. It's sort of smoothly that's position X. The matter wave might be in what we call a wave packet, where it's got a peak here that's sort of smoothly rounded off. And if this is telling you probability, really it's probability amplitude. You've got to take the complex conjugate square to get the probability. We won't worry about that. Basically, probability here. Where is this particle most likely to be? Right there, right? Now, notice that you get a little bit of wiggle room here. It's not unlikely to be right over here or over here. So you've got some width of where it's likely to be, but it's really not that likely to be over here, and it's not that likely to be out here. So you can measure, Gaussian distribution. You can talk about the width of the Gaussian. These are not always Gaussians themselves, by the way, but you can talk about. Let's say that that's the width there. Once the probability falls off to some fraction of the peak, the maximum, then we can say, well, it's probably within this amount here. So let's say that the width of this wave packet is delta x. Since this is probability, delta x tells us the uncertainty in our knowledge of where it is. If we know more precisely where it is, that would be a wave packet of a particle where we've nailed down its position to just that tiny range there, with some small probability of it being elsewhere. See what I mean? All right, so the more sharply peaked the wave packet is, the better we know its position. Now, the thing about these wave packets, these wave functions in general, is that they can be expressed in position or in terms of the momentum. So, we will also have some uncertainty in our knowledge of its momentum. Now, I'm going to put a subscript x on the momentum because we're dealing with just the x dimension right now. The same thing holds true for y and for z. So here, the particle is most likely to have a momentum under the peak, again. But again, it's a rounded off kind of a peak with some width to it. So there's some uncertainty in what its actual momentum is. We can't say exactly for certain what that momentum is, but we can narrow it down there. Okay? Now, where do we go from there? Well, that was a great thing itself. With a bit more work, Werner Heisenberg figured out that our knowledge of the position is related to our knowledge of the momentum. These are not truly independent things. You can't know one without saying something about the other, whether you can say that you don't know at all or you know to some extent or whatever. And so it turns out that, let's say that we can improve our measurements. With better instruments, perhaps we can narrow down our knowledge of the particle's position. And maybe with better instruments, we can narrow down our knowledge of the particle's momentum. We can sharpen those peaks. Well, you can keep doing that and getting better and better and better, only up to a point. And Heisenberg said that the uncertainty in position times the uncertainty in momentum must be greater than or about equal to h bar over 2. Now, h bar is h over 2 pi, where h is Planck's constant, which is the scale of quantum mechanics. And Planck's constant is very, very small. It's equal to, let's see here, 1.055 times 10 to the minus 34th joules times seconds. A really small number, which means we can actually get good measurements of things much better than the scale of normal everyday life anyway. But there's still a limit. So, the most precisely that we can know both momentum and position simultaneously is, let's take the greatest precision we can get. That means, I don't care about if these uncertainties are bigger, but let's get them where they're equal to the smallest amount. Delta x, delta p sub x, about equal to h. Notice I think I've rounded off that factor of 1 over 4 pi. We're making an estimate. So the best we can do, the best case is delta x, delta p x is about h, about equal to Planck's constant, to within a factor of 1 over 4 pi. All right, that's the best we can do. So how does that allow us to count the number of states available? I'll show you here. know what I really need is something like a ball boy in a tennis match, where you get someone to go and pick up the balls that go out of bounds so the players don't have to keep chasing after them and slowing the game down. I need someone to come up and clean the chalkboard as I'm starting to come back over here so I can just smoothly go through this. Okay. To show how this allows us that this product of the uncertainty in X and in P are limited, allows us to count actual numbers of states in what look like it be an infinite number. Let me take it to one dimension. So I've got there is position space, it's just the x-axis. Now, in 3 dimensions, I've got a limited volume that I'm dealing with. So in 1 dimension, it's a limited length. That's 1-dimensional volume. There are the walls of my box in 1 dimension. Now that box has a size L. L stands for length here. So how many different places can the particle be in the box? Well, since a particle is really a wave packet, according to Louis de Broglie, I'm asking, how many different ways can the wave packet be that are distinctly different? For example, maybe the wave packet peaks over here on the left-hand side. All right, that's one state it can be in. Now, I can also make a wave packet be like that. Notice where it's not really overlapping all that much. That's a different state for sure. But what about if I made the wave packet be like there? You see, it's so overlapping, the first wave packet, it's not really different. There's so much overlap in where it could be within that mostly you're just recounting all the states that you covered in the first wave packet. You see? So if I want to make truly distinctly different states of the wave packet, I'm going to put it where I'm crowding up the peaks where they don't really overlap much except on those narrow tails. Not that I've drawn it perfectly evenly, but you see here, I've got an actual discrete number of different position states the wave packet can be. Where I don't have them overlapping, but just a little bit, and they're filling up all the space. So the width of the wave packet is delta x, and I've got a total length L, which means the number of different position states is total length divided by the length of the packet. L over delta x. Let's look in momentum space. Exactly the same thing happens because I can write out the wave packet in momentum space too. If I know what volume I've got in momentum space, well, that's a length in 1 dimension again. I'll call that length L sub p for length in position space. Okay, and here are the different different states the wave packet can be in that are distinctly different. Each one with some width, and that's probably too small for y'all to see, delta p sub x. So the number of momentum states is I'm abbreviating here. L sub p over delta p sub x. Okay, now I've counted up number of position states, number of momentum states. What I want is the multiplicity of the whole thing. I take the product of the two. Number of position states times the number of momentum states. So the multiplicity, the number of total states available to one particle, that's the subscript 1, is equal to the product of L over delta x and L sub p over delta p sub x. And notice what happens in the denominator. When I multiply delta x and delta p sub x, remember what I said before, that we want to take it where we have the best possible knowledge, which means delta x, delta p sub x is h, Planck's constant. There. So now I have the multiplicity for one particle in one dimension. Of course, what I've actually got are 3 dimensions. So in 3 dimensions, so this was 1D. Now in 3D, I've got this for x, this for y, this for z, and this will term here for p sub x, for p sub y, for p sub z. I'll multiply all of those together. Where again, V sub p is the volume and position in, momentum space. Delta x, delta p sub x is h. Delta y, delta p sub y is h. Delta z, delta p sub z is h. Heisenberg's uncertainty principle applies to every axis individually. So I've got h cubed in the denominator. All right, last page of notes for this derivation. I've only done this for one particle, and that's actually a nice step there. This tells us quite a lot. Now, I can do exactly the same thing for every other particle in the gas individually, and I'll get the same result for them individually. But what about when I'm looking at 2 particles together in the box? You see, in this case, the total number of states available includes the total number of states for one particle and the total number of states for the other. Furthermore, they can now exchange energy between the 2 of them. If they bounce off of each other, the energy of one can be transferred into the other, and vice versa. So, I have a constraint on the total energy, but I don't constrain the individual energies. Okay, giving myself here. Okay.
You said that's in the 3 dimension, the total state is constrained, but the individual particles are not?
It's not for 3 dimensions, it's for multiple particles.
Okay.
All we are now just going to be dealing with the 3-dimensional case. So for a gas of 2 particles, the momentum space, well, we still got the same, we've got the product of their individual position spaces to count up the number of states. All the states available to one particle times all the states available to the other. All the momentum states available to one times all the momentum states available to the other, but with the exchange of energy. So the radius of the momentum space sphere is a little different. Now we have p sub x of particle 1, p sub x of particle 2, p sub y of particle 1, p sub y of particle 2, p sub z of particle 1, p sub z of particle 2. We have 6 dimensions. A 6-dimensional parameter space that we've constrained the total energy for So now, let's see here. P squared equals, let's see here. Since kinetic energy, or total energy now, is P squared over 2m, and the radius is the total momentum of the two particles together, then the radius is, let's see, the 4I squared. Yeah, I'll do that. There's your radius. This is total for both particles. So that is the square root of p sub 1x squared plus p sub 2x squared plus p sub 3. Oops. P sub 1y squared, there we go. P sub 1z squared plus p sub 2x squared, p2y squared, p2z squared. Excuse my messy handwriting, we'll have to give up what I'm saying. So it's a six-dimensional momentum, not a sphere, a hypersphere now. Hyper meaning extra dimensions. So the number of states available is going to be, now we've got the same volume for particle 1 and particle 2. We've got to multiply all the states for each one of the particles together. So we're going to have, remember before we had V times Vp over over H cubed. So now we've got V of 1 times V of the second, that's V squared, over H cubed times H cubed, so that's H to the 6th power. And for momentum, now we have the 6-dimensional momentum hypersphere. How do we calculate the volume of that, of the thickness of the surface area there? We have a formula in the back of the book. It's in the appendix, A sub D, the area of the surface area of a D-dimensional hypersphere for the momentum here. But we've got a counting problem again. Just like when we're counting up states on the different ways you can arrange quanta in an Einstein solid, we've got to avoid over-counting. If these two particles, if you can't tell them apart, which is generally the case, then if I've got, here's my volume. If I've got particle 1 here and particle 2 over here, is that any different from having particle 2 up here and particle 1 down here? No, because if they're identical particles, the system doesn't care which one is where, as long as we've got one particle there and one particle here. These actually are the same state. So to avoid over-counting the number of states for indistinguishable particles, let's see, how I counted it here is if they are distinctly different. What I really should do for indistinguishable particles, I have to divide by the number of ways of exchanging them. 1/2 in this case, since there are two particles. In general, for indistinguishable particles, we have to divide by n factorial ways that they could be exchanged. There's the 1 over n factorial, the ways that you can exchange them. times volume to the nth power, because you're just multiplying up the number of places one can be in versus another one being in, over Planck's constant to the 3n power, because each one of those n particles has h to the third in there, times this formula for a d-dimensional hypersphere, where you look up in the back of the book what that is. This is called a radius r when you look it up in the formula. And the formula is two times pi to the d over 2 all over d over 2 minus 1 factorial and all times the radius to the d minus 1 power. D is the number of dimensions of space you're dealing with, and r is the radius, which in our case will be p. This is in the back of the book. There's no point memorizing it, but I will note, if you're dealing with a two-dimensional space, so if d equals 2, what you get out is the two-dimensional area. I need to move this over again. The two-dimensional surface area of the surface area of a sphere in 2 dimensions is, do all of that math, 2 pi r. What do we normally call that? The circumference of a circle. A circle is a 2-dimensional sphere. Its surface area is just called the circumference. In 3 dimensions, you do all the math here, 4 pi r squared. The surface area of a 3-dimensional sphere, a plain old sphere, is 4 pi r squared. And you can go on up to 4 dimensions and so on like this. Okay. When you put that in, and you note that the radius of this momentum hypersphere is the momentum, which is equal to the square root of 2nu. This is the total momentum of all the particles together. Then you come up with one over n factorial, v to the nth power over h to the 3nth power times all of this stuff here. Let's see. That radius is square root of 2mu. Let's see. What number of dimensions do we have? The number of dimensions is, let's see, 3n. 3 dimensions of space times the number of particles. And so I should have put that right up there. So we'll make a little room here. So let's see. We'll take the square root, d minus 1, so that's 3n minus 1 all over 2. And in practice, since these are going to be very large numbers, we can drop some of these terms, like that and this here, and we can get an approximate formula that works really, really well. 1/n factorial, v to the nth power over h to the 3n times pi to the 3n over 2 divided by 3n over 2 factorial times 2mu to the 3n, and we can drop that minus 1, 3n over 2 power. That is a horrible, ugly mess. But what we're going to see is that in practice, we're going to care about some parts of this at some times and other parts at other times. And we can pull out the important factors. The multiplicity is a function of the total energy, the volume, and the number of particles. And that is equal to some horribly ugly function of the number, which has all those factorials in it. Remember, we don't like factorials. We'll eventually use Stirling's approximation by taking the log, natural log, and we'll get rid of those. Times v to the nth power times energy to the 3n over 2 power. And we'll just deal with this function of n when we have to, but most of the time we don't need to. Well, sometimes we do. That's how we get the multiplicity of a monatomic ideal gas of n number of particles.